Lots going on. We're getting close to the end of the semester, so let's review some of the announcements in detail just to make sure we're on the same page as far as scheduling goes. Monday's class is going to be online, so I'll send you a link of the recorded lecture. That probably won't be today. That will be before Monday during our class time, but I'll post the link on Blackboard and also send it out via email. If you look at the syllabus, quizzes account for 3% of our course grade. So far we've had 2 quizzes. We'll likely have 1 more before the end of the semester. So just want to give you the general heads up about that. Homework 12 is due before class on Friday, April 12th. I've prepared that. I don't remember whether I posted it already, but if I haven't, I'll do it this afternoon. It's just 2 problems, so I don't think that'll be too much additional work for you. The final report associated with the design project is due before class on Monday. And I've got a slide here in just a second where I wanted to emphasize a few things, but to reiterate what I've mentioned before, that final submission should be more than just pasting together what your previous draft submissions were. You should be making adjustments, enhancements, improvements along the way. And so the final report should really be a polished professional project that you could think of as maybe a portfolio item that you could show to future employers, something that you think represents the maximum you're able to achieve, something you're proud of. So that's due before class on the 15th, and then our final exam is scheduled for the 23rd from 10:15 to 12:15. So any questions about those scheduling items? All right. Today we're going to begin talking about some concepts from chapter 14 in the book. And I think it's really valuable for you to spend some time reflecting on the material outside of class. Review the way that the author presents this information. Because if you hear it from 2 different perspectives, you're more likely to understand it and retain it. So we're going to be talking about gradually varied flow. Here's that slide. I wanted to just emphasize that there are detailed written instructions in the handout. And I was a little bit surprised at how many people in Phase 2 didn't know that there were restrictions on which pipe diameters you're allowed to use. Some people used pipes like 231 millimeter diameter. And I mean, I applaud them for wanting to really be precise about what was the optimal pipe diameter, but you're not going to find a commercially available pipe in every imaginable pipe size. And so that's just an illustration of there could be some specific instructions in the handout that you either haven't noticed or forgot. So before that final submission, you should read the whole thing from beginning to end, the entire handout, and especially the instructions that are related to the final report. And so here in yellow, I've highlighted the point that you need to illustrate how your design has changed. And so as you're writing the text with your final report, talk about what improvements you've made from your draft submission until the final product. And so don't just have, for example, your updated calculations for demand estimation, but have the updated calculations for demand estimation, and then also in the write-up related to demand estimation, have a specific section where you say, here are the corrections and improvements I made beyond Phase 1. So I'm going to go back and look at what were my previous comments. I'm going to go into the grade book and see what did I tell you should be fixed, and then I'm going to check to see if it did get fixed. Okay, any questions related to the project? All right, gradually varied flow is what we're talking about today. Where we've been recently is RVF. Does anybody remember what the R in RVF stands for? What have we talked about the last couple of lectures? Oof, we should have had the quiz today.
Rapid.
Pardon me?
Rapid.
R is rapid. Good. Rapidly varying flow. Hydraulic jumps is what we've been talking about recently. Hydraulic jumps is just a really dramatic increase in the depth of flow. Gradually varying flow is a lot more common than hydraulic jumps. We do see hydraulic jumps Like we mentioned before, flow out of spillways. We see hydraulic jumps sometimes in the rapids of a river. But hydraulic jumps are kind of an uncommon thing. Like when you see one, you'll be pleasantly surprised. You'll take note of it because, oh, it's kind of an uncommon thing to have rapidly varying flow. Gradually varying flow is all around us. It occurs almost everywhere. You'll remember that Manning's equation applies when steady is flow and when flow is uniform and steady. So in a prismatic channel, where it has plenty of time to reach an equilibrium depth and where the flow rate isn't changing, that's where Manning's equation applies. That happens sometimes, but gradually varying flow is what we often usually see in nature. So here's a depiction of a meandering stream. And as the stream gets deeper in some spots, as the slope is changing, as the channel gets wider and narrower, then the depth is just constantly on the move. It's changing. It's getting deeper in one section, shallower in another. And so we need some sort of a method that can predict for us what will be the new depth, upstream or downstream. So if we know, for example, what's the slope of a section and what's the depth at one location, we want to be able to predict if you go a certain distance upstream, then how deep is the water going to be? It's on my mind right now because there's kind of high water in some streams in the area. It's been wet the last few days. And one of the rivers that I'm interested in is the Mud River. It flows through Milton, it flows through parts of Ona, and I think into Barbersville. But the nearest stream gauge that I know about on the Mud River is in Milton. And so we can measure the depth of the Mud River in Milton, but what if I want to know the depth of the Mud River in Ona, several miles downstream? We have to have some technique to extrapolate the depth at one location to a different location of interest. And so that's what we're going to be working towards today and then next week, is learning some methods for predicting depths at locations that we don't know it, where it's not being directly measured. So gradually varying flow can be between two uniform flow sections where it's just making a gradual transition between them. It can be induced by hydraulic structures which are man-made. And it can be due to naturally occurring objects in the water, like steps or waterfalls or obstructions, slope changes. And so as the depth changes, so do other flow characteristics like the velocity. Like this narrow section of the stream, it's likely that the velocity is faster through that narrow section of the stream than it is through this section, which is wider. And I don't know if you can tell from the image, but it seems like the depth, that maybe there's a sandbar here where it's very shallow in one place and deeper in the other. So flow is pretty complicated, and we're going to make some dramatically simplified assumptions to be able to do just some basic calculations to try and predict depths up and downstream. And some of the simplifications and assumptions we'll make is the pressure distribution is hydrostatic. We're also going to continue with the assumption that I mentioned with rapidly varying flow, that we have a uniform velocity distribution. And that's the one that maybe is like nails on a chalkboard. If we're assuming that in a river, where in reality we know that the flow is fastest at the top of the stream and that the velocity decreases as we get closer to the bottom. For simplification, when it comes to these calculational techniques, we sometimes have to assume that the flow velocity is just constant with respect to depth, that it's not slowing down as we get closer to the bottom of the channel. So there are a few things that we're going to want to be able to just look at and know what kind of a water surface profile we have. There are these abbreviations that we're going to learn whether we've got an M1 profile or an S1 profile. There's different zones and different classifications depending on the slope of the stream. So we'll get into that a little bit later, but here are just a few illustrations similar to where I showed you previously things that could cause a hydraulic jump. These are things where we could see gradually varying flow. And so you'll see that if you have an underflow gate, where there was pooling upstream of the underflow gate, then the water is deeper than it normally would be. Here in the uniform flow, where we have the normal depth, which is just calculated by Manning's equation, the flow is no longer uniform if we have an obstruction like a gate. So there's pooling upstream, so the water is deeper than it normally would be because of that pooling, and so it would gradually be increasing the depth as you approach the gate. Or if we had water flowing off the edge of some drop, you can see how that would be reducing the depth. As you get closer to the drop, then the flow depth is decreasing. And you couldn't predict that with Manning's equation. You know, if you knew the roughness of this channel and if you knew the slope of the channel, you can calculate the normal depth, but the normal depth doesn't apply because there's some other situation that's drawing down the flow. And so the gradually varied flow depth at a certain location wouldn't be predicted by the critical depth. It's not predicted by the normal depth. None of the equations we've learned before, like the Bellinger momentum equation, wouldn't tell you what's the depth at a certain location. It's not a hydraulic jump. So, I mean, you can plug numbers into a formula, but the formula may not apply. And this is the case where so far none of the methods or equations we've learned would be able to predict how the water depth is getting shallower and shallower and shallower until it finally flows over the edge of that drop. If we had two slopes, like a steep slope that's matching up with a less steep slope, and by steep I don't necessarily mean supercritical slope. I mean it's relatively steeper in this section than it is in the other. So we're not having supercritical flow go to subcritical flow, because if that was the case, it would go through a hydraulic jump. But this is just subcritical flow and even more subcritical flow matching up. There would be a gradual transition in depth between the two sections. Or if you have a steep slope and water flowing under a gate, it's going to stay supercritical if it's a steep slope, meaning a slope that's steeper than the critical slope. Water flows from under the gate at supercritical conditions, but it's staying supercritical, so the normal depth downstream, if this slope is a steep slope, is still going to be supercritical. So it would gradually increase in depth until it matched back up with the normal depth downstream. So for the equations we're going to apply, we assume that we have a prismatic channel, meaning that we could draw a mirror image about the center line, and it's the same on the left-hand side as it is on the right-hand side. We're going to assume steady flow, so not uniform, but steady flow means that the flow rate is not changing with respect to time. The bed slope is relatively small, so this just allows us to assume that the horizontal distance is the same as the inclined distance. And then here's this really tricky kind of unpleasant simplification here, a uniform velocity distribution. We'll get over it though. There's other ways to more sophisticated approaches if we really need the precision where we could get around that assumption. The kinetic energy correction factor, you may remember that if you had laminar flow, then the kinetic energy correction factor is 2. We won't have laminar flow. Anytime the water is moving in typical conditions, you have turbulent flow. So we'll just use the kinetic energy correction factor of equal to 1. So that means that the velocity head doesn't need to be adjusted anything beyond just its natural calculation. Hydrostatic pressure distribution, parallel streamlines, and we're going to assume that between 2 points that we're interested in, that the channel is rough to the same degree. So we're not going to introduce a change in the bed type between 2 sections. So we wouldn't have gravel in one section and then sand in the other and try and calculate the change in depth between those two. We'd have to break it up into smaller pieces if we have a change in the material and the roughness in the direction of flow. Okay, so look at this cross section. This is already, just by inspection, we can tell this is not uniform flow. What are the clues that this is not uniform flow? Does anybody see the clues of how we could tell that conditions are not uniform here? Okay, good. Velocity. What about it?
It's changing.
It's changing, right. Upstream, the velocity is v. Downstream, the velocity is v plus dv. So the velocity changed. That by itself is maybe the definition that we have non-uniform flow. Why did the velocity change? Well, I guess it's a chicken and the egg thing. You could say that the velocity changed because the depth changed, right? Because downstream upstream it was y, downstream it's y plus dy. Or we could say that the velocity changed because the depth changed, or the depth changed because the velocity changed. I mean, it's the relationship is linked together. So basically, for me, the clue that we have non-uniform flow is to look at the slopes. There's 3 slopes here. S sub f is the slope of the energy grade line. So this dashed line above the water surface, remember, represents the velocity head that's over and above the energy that's associated with the depth of flow. So here it's called TEL, total energy line. Sometimes we also call that the energy grade line. So the energy grade line slope, S sub f, is not parallel to the water surface slope. And the water surface slope is not parallel to the channel slope. When we have steady, uniform flow, all 3 of those things are parallel. So the slopes are equal. In uniform flow, S naught is equal to S sub w, and that's equal to S sub f. But here, you can tell just by looking that those are all on different slopes. So this is a non-uniform flow. The flow is gradually getting deeper downstream. So you can see there's an increase in depth compared to the upstream location. And if we want to kind of calculate the energy at any particular location, then the specific energy is the depth and the velocity head. And then the other thing that we want to be aware of is that the change of energy with respect to a change in depth can be estimated with 1 minus the Froude number squared. So if we combine those 2 things together and then substitute in the slope of the energy grade line for the change in head with respect to length, and the slope of the channel bottom that's by definition the change in the elevation above a datum. So z was, if we have some vertical datum, z is the distance from that vertical datum up to the bottom of the channel. So you can see that as the water's flowing downstream here, z is decreasing, and also the water surface elevation is decreasing, and the energy grade line height is decreasing. So this equation says that we can calculate how the water depth is changing with respect to some distance downstream. So this is, in words, this dy dl is a rate. It's the rate of variation of depth of flow, so dy, depth of flow with respect to distance along the flow direction. So that's dl. So at a point, just at a certain location, at a point, we could use dy dl to find out what's the slope of the water surface. And specifically, the slope of the water surface is the channel slope plus dy dl. Now, S naught is going to be negative. And we put a negative value in there if the water's flowing downstream. So this is one of those times where we don't take for granted that S naught, it's not implied in the formula that it is downhill. So downhill is negative when we're trying to find out the slope of the water surface. So let me show you some implications of all this. This rate of variation of depth of flow with respect to distance. Here's the classical problem in gradual varying flow. The classical problem is we've got water at a certain location where we know the depth because we measured it here. So we know the depth at location 2. And let's say that we know a certain distance upstream and we want to find out how deep is the water there. So if you had a measurement of the Mud River in Milton and you wanted to predict how deep is the water a mile upstream, so you know the distance, the question is, what's the depth upstream? So this classical problem of gradually varying flow, we can use this dy dl to find the slope of the water surface, but only at a point. And so here's kind of the problem, is this is going to tell us the slope of the water surface at a point, but you can see that the water surface is gradually, its slope is changing between the 2 points. And so we couldn't use the slope of the water surface just at a single point to jump all the way upstream, because if we did that, if we tried to find the upstream depth by just knowing the slope of the water surface at a single point, we'd extrapolate that slope and it wouldn't match up with this downstream depth location. So you see, if we extend the slope over a really long distance, we can't approximate a curve with a line, not over a big distance. We can get away with approximating the curve as a line if we break it up into smaller pieces. So what we're going to do starting on Monday is there's a method where we can use this formula, which tells us the slope of the water surface at a single point. We're going to use this formula for just small steps. And so we're going to say, let's use that formula over a small step. And it's not so bad if we approximate this segment as a line. I mean, it's a little bit curved, but it's okay if we approximate a small segment as a line. And then we'd find, how far is it between these 2 points where we know the 2 depths, or we could say if we know the length and we know the depth here, then we could find the next depth upstream. So we have to know 2 of the 3. We have to know a depth and a distance to find the other depth, or we could know both depths and calculate the distance between them. But the point is, if we break it up into multiple steps and we find out the slope of the water surface for each of those segments, then we can actually have sufficient accuracy to make a worthwhile prediction. So that's going to be the step-by-step method, sometimes also called the direct step method, that we begin on Monday. But it all comes down to an application of dy dl. So let me pause. Are there any questions so far of the concepts, or like what is the classical problem we're interested in?
What exactly is like the metric for separating rapidly varying flow from gradually?
Yeah, so what's the difference between rapid and gradual? Well, rapidly varying flow would involve a hydraulic jump, but there are other things. You probably noticed that this was classifying as the water was going off the side of the cliff that it was rapid, right? So I don't think that there is like a cutoff point for how rapid the variation has to be before we call it rapidly varying flow. What I'd say is, if it's a hydraulic jump, that's rapidly varying flow. And maybe it's also rapidly varying flow if the direct step method and the standard step method, like if we're no longer getting accurate results because the depth is just changing too quickly, that's probably rapidly varying flow as well. Once you get off the edge, when there is no longer a channel bottom, that's rapidly varying flow. But that's a good question, because you'd expect that maybe there'd be, in the same way that we have a discrete threshold for Froude number. Froude number of 1 separates supercritical and subcritical. Or in the case of the Reynolds number, where 4,000 and above is turbulent, 2,000 and below is laminar. Like, those are real quantitative thresholds. I don't think such a thing exists in classifying whether it's gradual or uniform, or gradual or rapid. Okay, so this is a glimpse of where we're headed, is applying this over lots of little segments. So this gradually varying flow equation, we're going to be looking at trying to predict the slope of the water surface. We'll have to know the channel slope and then dy dl for a certain segment length. So we'll limit either the dl if we're trying to calculate dy. So we'll limit the dl distance so it's not too long. Or we'll set a threshold for how much of a dy is acceptable to calculate the distance dl. So there's a couple of simplifications that can make our lives easier depending on if we have a rectangular channel or if the rectangular channel is wide from a technical standpoint. This dy-dl formula, the slope of the energy grade line here, S sub f, the slope of the energy grade line, we get that by using Manning's equation. So we can rearrange Manning's equation, which it's Q equals area to the 5/3, slope to the 1/2 divided by n times p to the 2/3. So we can rearrange that to solve for s. And the s in Manning's equation, normally, if we're using Manning's equation, we have steady uniform flow. And so it's the slope of the channel bottom, and it's also the slope of the water surface, and it's also the slope of the energy grade line. But when we use it with gradually varying flow, what it actually calculates for us is the slope of the energy grade line, so S sub f. So here in this dy-dl, S naught is the physical slope of the bottom of the channel, and then S sub f is the slope of the energy grade line, and we're going to rearrange Manning's equation to find it. So we've got an example in a moment where that's what we'll do. We'll rearrange Manning's equation, we'll solve for S sub f. So that being the case, we could substitute in Manning's equation here in SI units. This is what Manning's equation looks like if you solve for S sub f and you've got a known velocity, a known n value, and hydraulic radius. And this is true regardless of what the shape looks like. It could be trapezoidal channel, it could be a rectangular or circular profile. If you've got a wide section, remember wide means that the width of the channel is more than 20 times greater than the depth. So if it's wide from that technical standpoint, then dy-dl simplifies a little bit, because then we could just use the normal depth and the critical depth as the parameters for calculating it. So they call this the process equation, or at least our book does. I don't know why they call it the process, but sounds like a pretty good nickname for an equation, so we'll go with it. This is what we'll use for a wide channel in calculating what is the slope of the change in water depth in the direction of flow. And if it's wide, then the normal depth is pretty easy to calculate. So this formula, y sub n, in terms of flow per unit width, n value, and channel bed slope, remember this one only applies if it's wide, and this one only applies if it's either rectangular or if it's wide, it also applies. But both of them would necessitate us calculating the flow per unit width, lowercase q. So let's try an example. Let's say we've got a rectangular channel carrying 20 cubic meters per second. It's 40 meters wide and 2 meters deep. So just in a beautiful coincidence, this meets the threshold of being a wide channel. So that's going to make it a little bit easier for us to calculate the critical depth and the normal depth because it's wide. We know the bed slope is 0.00015, and it says that's down. So because that's downhill, then that means that when we use the S naught here, the S naught is going to be negative. Okay, when we want to calculate the water surface slope, then we'll use a negative S naught there for this water surface slope part. But I'm going to pause and let you calculate what is dy-dl. So to do that, you're going to need to calculate the critical depth and the normal depth, and then the y that it's talking about is the depth at the location that we're interested in. So at the location where it's 2 meters deep. So y is given as 2 meters. Find y sub c, find y sub n, and then put it into the process equation to find dy-dl. So first find y sub c, then find y sub n, then find dy dl. Okay, so hopefully you've got your calculator with you today, some scratch paper. Let me just interrupt you briefly for one clarification. So when you use S naught in this formula, just put in the value without the sign. But then when we find the water surface slope, then include the value and the sign of S naught. So obviously S naught is downhill. The water flows downhill. Our channel is sloped downward. But when you're finding dy dl, just put in the magnitude of the slope and not the negative sign. Okay, as I was circulating around looking over your shoulder, I saw people seem to be headed on the right track there. The critical depth should be 0.2943 meters. And then when we invoke this assumption that the channel is wide, we can calculate the normal depth a little bit easier than usual. And the normal depth is 0.912 meters. So now given that, we can substitute it into the process equation for dy dl. And if you do that, the slope of the channel, we're just putting in the numerical value, not the sign, so 0.00015. And then we got to make sure not to introduce a calculation error here. The numerator has this y sub n divided by y term to the 10^3 power, and then the denominator, where we've got the ratio of the critical depth to the depth, that's to the 3rd power. It's easy to make mistakes. My recommendation is to keep a scratch paper and write your intermediate calculations along the way, double check, triple check as time allows. But what we get here is that the dy dl should be 1.39 times 10 to the 4th. So that's a positive value, and it means that the water is getting deeper downstream. So the dy is increasing. So the water depth is getting deeper in the direction of flow. By the way, before we move any further in this example, does anybody have questions on critical depth or normal depth or the process equation? Okay, so it asked, is the depth increasing or decreasing in the direction of flow? So dy dl is saying if you're going downstream, is the dy getting larger or smaller? And it's similar to what we see here. In this diagram that's on the screen here on the left side, the depth was increasing, and that's because we've got a positive dy dl. The example also asked, what is the water surface slope with respect to horizontal? So if we want to find S sub w, now that's where we use the dy dl that we just calculated and combine it with the downhill bed slope. And so let me show you what that looks like. This is just a little sketch that I made showing that we have a critical depth of 0.29 meters, a normal depth of 0.91 meters, and then the actual water flow depth is greater than either of those two. That's a preview of diagnosing the water surface profile. So the fact that the normal depth is greater than the critical depth means that it's a mild slope. And then the fact that the flow depth of 2 meters is greater than either of the other two, it puts it in a location that we'll know to be as zone 1. So that's an M1 profile. We'll talk all about that in just a minute. But here's the water surface slope. The water surface slope is negative. So, if you consider it relative to horizontal, then the water surface slope is downhill, even though the water is getting deeper. And that's because the channel slope is steeper than the rate that the water depth is increasing. So that's why we have dy dl is 1.39 times 10 to the fourth, but the channel slope is negative 1.5 times 10 to the fourth. So of the two, the channel slope is more negative than the water surface, than the dy dl is positive. So relative to horizontal, I guess this figure is another good illustration of it. We can tell that the water is getting deeper in the direction of flow. You can just see it. It's getting deeper, but the water surface slope is still downhill compared to horizontal. Compared to horizontal, the water surface slope is pointing downward. So it's not like the water surface slope is positive in this case. It's still negative. So the water's getting deeper, but yet the water's still flowing downhill. So that's how we calculate S sub W. Any questions before we move on from that example and look at some of these water surface profile types? All right, so it's important when classifying the water surface profile to calculate the normal depth, the critical depth, and compare it to the known depth at a certain location. And it's useful to know the water surface profile because you can understand whether the flow is increasing or decreasing in the direction that you're interested in just by knowing the water surface profile. And you sometimes can infer the cause of the gradually varying flow by the water surface profile type. So the first thing that we do is we look at the bed of the channel. So a mild slope, or classified as M, is if the normal depth is greater than the critical depth. And you already know this. You know this from specific energy diagrams. You know this from momentum depth diagrams. The idea that if you have the normal depth is greater than the critical depth, you previously have called that subcritical flow, right? Well, what kind of slope causes subcritical flow? A mild slope. So that's why we're calling this mild when the slope is less steep than the critical slope. Or we also know it if the normal depth is greater than the critical depth. So a steep slope is the opposite of that, when the flow depth is less than the critical depth. So you can see normal depth less than critical depth, that's steep. Critical is when the two are equal. Horizontal and adverse are these kind of fringe cases that you'll almost never see, but technically they do exist when we could classify water surface profiles for if a channel is just temporarily horizontal through a section, then we'd know that there is a critical depth we can calculate. There's no such thing as a normal depth, though, if we have no slope. Same thing is true if water's flowing uphill briefly, then you can calculate the critical depth for those flow conditions, but there would be no corresponding normal depth. So the profile type is first classified by what type of slope you've got: mild, steep, critical, horizontal, or adverse. The next thing you do is you look at where is the flow depth with respect to one of three zones. So if your given flow depth is bigger than the critical or normal depth, that puts you in zone 1. If your given flow depth is between them, that puts you in zone 2. Or if it's smaller than either normal depth or critical depth, you're in zone 3. So those are the three zones. You kind of just need to memorize this. It's important. On the final exam, you're almost certain to have a problem where I ask you to classify the water surface slope. So I'll ask you to, I'll just say that. I'll say, determine the water surface profile. And so what that means is you'll have to first figure out, is it mild, steep, critical, horizontal, or adverse? And then you'll have to see, is the given flow depth greater than the critical and normal, between the two, or less than critical and normal? So if you've got a positive dy dl, you can see that the water depth is going up compared to horizontal. Decreasing, it's getting shallower in the direction of flow. If the water surface slope in the direction of flow, if dy dl is 0, then that means it's uniform. Infinite means water's flowing over some sort of an edge. All right, this is really important. M1 profile is when the given flow depth is greater than critical, which is the dashed line here, or normal depth, which is the solid line. M2 profiles are going to be decreasing. So you can see that the flow is getting shallower if it's an M2 profile. An M3 profile is like flow from underneath an underflow gate. You've got a mild slope, but supercritical conditions, it's going to be gradually increasing before it goes through the hydraulic jump. Here's the typical water surface shape associated with steep slopes. An S1 profile is when the flow depth is greater than the critical or the normal. So compare the M to the S's. Look, when it's the M profiles, the normal depth is that top line, and the critical depth is below it. But for the steep profiles, it's the critical depth that's on top, and it's the normal depth that's beneath it. And then the actual given flow depth could be anywhere. It could be above both of them, it could be between them, or below both of them. And you see the corresponding S1, S2, S3 designations, depending on which zone the flow depth is in. Here are the critical, horizontal, and adverse. So you'll see that there is no C2 profile, because if you've got critical depth, then the normal depth is the same. If you have a critical slope, then the normal depth and the critical depth are the same. So you can either be above them both or beneath them both, but there's no distance between them, so that means there's no zone 2 for a critical slope. In a horizontal, there's no H1 because there's no normal depth. And same thing with an adverse slope. There's no A1 because there's no such thing as a normal depth if you've got water flowing uphill. Here's the final thing we'll look at today. This is some of the things that could cause different types of profiles. So you could have an M1 if you had an obstruction, like a dam. And so this dam is causing pooling. And so the M1 profile is the water that's getting deeper in the direction of flow as it approaches some sort of an obstacle like a dam. Or an M2 profile could be caused by water flowing over an edge. Or an M3 profile could be caused from water under an underflow gate prior to the hydraulic jump. Steep slope causes would be if we have a steep slope, means the slope is greater than the critical slope. And then if you had water approaching an obstruction, it would go through a hydraulic jump because it's going to be going subcritical briefly. So an S1 profile is where you have subcritical flow on a steep slope. So what would cause that? Some sort of an obstruction that induced pooling. So similar to this middle diagram here, S1 is where you had subcritical flow on a steep slope. So it would have to be some sort of an obstruction for that briefly to occur. And then it goes through S2 as it's drawing back down again and reaching its normal depth. Adverse and critical I don't want to spend too much time on because they're kind of fringe, unlikely things, but you could see what would potentially cause an adverse 3 profile would be supercritical conditions on an uphill slope. So it would be an underflow gate that's approaching a drop-off where you had an uphill slope. Okay, let's leave it there for today. This is just a couple of other figures describing water surface profiles. We'll take another look at those on Monday. You've got plenty to keep you busy. Class on Monday will be online, so look for the link with that. We'll probably have a quiz on Wednesday. Friday, you've got homework 12 due, and all the rest of it. All right, well, have a good weekend. We'll have that recorded lecture on Monday, and I'll see you face-to-face again on Wednesday next week.